Okay. Okay, it's 6 p.m. So my name is Daryl. I'm a tutor at the ARC as well as a materials grad student. So I should know this stuff really well. This is your first exam, is that correct? Okay. So this is, I think this email was sent to you from Professor Calland as well, so I'm just going to kind of go step by step as well as do notes for each section. I'm not going to spend a lot of time on bonding types and characteristics. That's pretty much basic chemistry and basic reading. So if you go look up online or you go look up somewhere, you can read up what the different types are. I believe there's ionic, there's covalent, there's metallic. There are at times dipole, so I don't know if you covered that in class. So I'm going to skip over bonding types and characteristics. Bonding force and energy curves, that's also pretty straightforward. If there are questions, please ask those at the end because I'm going to spend time on some other stuff. So I'm going to start with ionic bonding rules. So if you remember, or don't remember, what ionic bonding rules are they're the ideas of how let me make sure if this is it. Yeah. So the ionic bonding rules are something you briefly covered, maybe, I don't know, he sometimes goes pretty fast on certain subjects, but it's the idea of the ratio of the, ratio of the cation for C compared to the ratio of the anion. So the ratio of the positive atom over the ratio atomic size, the radius of the atomic negative atom. So if you remember, there was a table in your chart that gave you a bunch of different listings and ranges, and the reason you always do this ratio first, or the reason why you do this ratio is because on the periodic table, so you have all these columns in here, you're going to have your positive anions on this side and usually your negative anions on this side. That kind of goes back to basic chemistry. So the idea is if you're on this side of the periodic table, remember that your atomic sizes are smaller. And so the reason we do this is for unity. So this should be always less than 1. The types are, so let me see, I believe there's dipole. So dipole is the idea that you have two nearest neighbors. Okay, so for two nearest neighbors, just remember when you do the ratio of the two, you should get 1.155 or less, and that's telling you have like a dipole situation, or you have a diatomic arrangement. Then you should remember that if this ratio is including the 0.155 up till, I believe it was 2.255. Then in this situation, you jump up to nearest neighbors of 3. So we can still draw these in a we can still draw these in a 2D plane to prove these to ourselves. So I have proved these to myself to make sure. So if you have questions of these later after everything, I can try to prove it to you again. So the next arrangement is more of a tetrahedron where we have 4. So again, now we have to include 0.255 based upon the proof, and our ratio then goes up to 0.41. 0.414. And this idea is 4 near neighbors with an anion cation combination. So the way that this is usually proved is easiest way to draw a tetrahedron is with a cube. So if I have an atom here, an atom here, and an atom here, and an atom here, and I connect all the diagonals correctly, I have a tetrahedron, and the atom is located in the middle. So that's how you prove it. So you got to remember this ratio, and then the last ratio, I believe. So this is for. Let's see. This was tetra. But now we get a little bit confusing because I believe the next one is. It's technically called octa, but it only stands for 6. So the next one we have is a ratio of 6, which how did I prove that? Anyway, you have to then go including this number for your ratio up until 0.732. And this is for 6 atoms, this is for 4, this is for 2, and this is for 1. So, ignoring. And then for 8, you have 0.732, including it, your ratio. And then because of the idea of unity that you can never really have in a cation atom with a radius larger than an anion, you should never, the theory goes, you should never be able to go above unity. Any questions on this?
What was the 0.732 to?
0.732 to 1.
Yeah, what's the name for that one?
I can't remember. This is for 8 nearest atoms. So I thought I had notes on it, but you need to remember, I think one of them is called octa, but it doesn't stand for 8. It technically stands for 6. So you got to just be sure to review that, review the actual coordination, how they call it, because it's more of a geometry term rather than a number term. Question?
No.
Question? Yeah.
What's the subscript?
R sub C for cation, and then R sub A for anion. Any other questions?
When you go to close pack, is that when you reach radius of 1, basically?
So remember, it's the radius of the sizes. So closed pack would probably be if you were doing some kind of like I don't know, because remember this is ionic ratios. So this ratio of 1 comes up with closed packed of like the same atom. I don't know who asked that. Sorry. Who asked that question? Yeah. Okay. So like if you had the same atom sizes, you would, when you do closed packed of whatever it is, BCC or whatever, then you would have a 1-to-1 ratio. The idea is though that they put this in here so that you can't go. It's in theory you can't go above it. So that I don't know if that comes from that, but also remember it's the periodic table, so you can't. You really shouldn't be able to go for anions and cations above it. Anything else about this?
Let me check online. Though for the person who asked online for the 0.155, that comes from proving the three nearest neighbors. So the proof goes that the lowest atomic ratio is 0.155, so that has to be the upper limit for the two nearest neighbors. And it should be 2 for 3, 4. Did I screw that up? 2, 3, 1, 3. One for 2. Yeah. Okay.
So yeah, so 2 nearest neighbors, sorry, 3 nearest neighbors, and 4.
4, then 6. Okay, so that covers the ionic bonding rules. We're gonna talk about the simple ionic crystal structures, but and the diamond cubic, but then I'm gonna talk about the actual just crystal structures in general. Which then I also talk about the ratio rules between the
lattice constant and the radius of an atom.
So I'll kind of go backwards, I guess.
So simple cubic, when we talk about repeating lattice structure in whatever material we're talking about, we want to talk about what's called the unit cell. So we're trying to pick a unit configuration that we can repeat over and over and over. So instead of looking at a very complex structure, which can happen in other materials, some materials have pretty simple structures. Maybe the atoms are not, they're different, but they're pretty simple. And that idea is for the simple cubic, which I think there's definitely only one natural simple cubic, maybe 2. Is the idea that you have a atom at each corner of your cube. So the total number of atoms, however, is 1. There's only 1 atom, because if we're only looking at the lattice structure, you're only taking up 1/8 of a volume inside the cube. So there's only going to be 1 atom. And in this case, they touch along the lattice parameter. So 2R of an atom in a simple cubic equals A, the lattice constant. So now we get to some other ones. So BCC. So BCC has 1 in each corner like the simple cubic. However, it has a body-centered atom in the middle. Since it has a body-centered atom in the middle, the closest packing is along the diagonal here. So from, how do I do this? I guess I'll do X, Y, and Z. So along the diagonal is the closest packing. So this diagonal length you can show to be square root of 3A if the length of the side of your cube is A, the lattice constant, which equals 4R. So then you can get a equation that relates your radius to your atomic space, the last parameter to your radius of your atom. So then we go to BCC. So then we go to FCC. FCC has face-centered atoms. So along every face, which will get really confusing if I start drawing them all in. Yeah, it has an atom along each face. So that means now they also have the corner atoms. So you have along each diagonal is the closest packing in an FCC crystal structure. So for this, that means now it's square root of 2a equals, there's still 4 r's. So now we have a equals 4r over square root 2. The number of atoms is going to equal an FCC 4. And the number of atoms here is going to equal 2. So in VCC, you're adding 1 full atom inside the volume of your cube, and then you still have the 1/8, you have 8 1/8 that add to 1, so you have 2. And then for the FCC, you have 6 halves of an atom, that's 3, and then you have the one that's the same as the simple cubic, you have all the corner atoms, so that's 4.
Any questions about that?
Could you go back to the other screen for a moment?
Yeah. So any questions about that? This is usually, yeah.
So what was A representing in the body-centered cubic and face-centered cubic? Is it still the total number of atoms? Or
This A?
yes,
This A is going to be the lattice constant.
the lattice constant.
Yeah, which is the length of the side of a cube for the cubic structures.
Thank you.
Yeah.
What's R then?
What's R? R is the, so each atom has a radius associated with it. That's the radius of that atom. So if you were to connect all the atoms, but if I drew them better and they were connected, you'd only have one R here, then you'd have 1 full atom here, so that's 2R. And then you have another R here, so that's 4. Same thing for here, except it's along a different diagonal now. Any other questions about that?
So then the email also meant, well, let's see, what did they have to say online? Yes. What's that? So simple cubic has 1. What if 2 atoms were different and you had different R's? So if 2 atoms had different R's, you wouldn't be in the closest packing, and so your lattice parameter would change. So that A that is
Will
seen,
we have to calculate that on the test, or?
I don't know. I don't think he does anything like that. I think you have to just worry about the closest packing. So for the simple structures. Okay, and so he mentions here HCP, which is the hexagonal closed pack.
I guess I can mention, because I don't know if he mentioned it, but he of course mentioned maybe if you had the marbles, right, or something like a round sphere, you can try to learn how to stack these on your own and learn how the stacking sequences work. So for HCP, there is a certain stacking sequence. However, I don't exactly remember how they stack them, but the idea for hexagonal, if you're looking straight down on the hexagonal, is you have, let's see here, so 1, 2, 3, 4, 5, 6, and then you have one in the middle. So looking down, you would see this. If you were to draw a 3-dimension, you could have seen them in the books, the textbooks. So I'm just kind of mentioning this. I don't think he would ask you. I don't know. Let's see. So we got 1 here. So that should be 6, right? 1, 2, 3, 1, 2, 3. So if you were to draw these down, you get the same atoms here. However, if you remember from the book, there's also an atom located, and it was in one of your homeworks too. It was to kind of prove where this atom height was. I think it was homework 1, that this is at C/2. So you have to remember in HCP, there's 3 atoms, but they are every other triangle, if you can imagine that or remember that. Does that make sense? Otherwise, I'm going to draw it fully. Does someone want me to draw it fully? Okay. So you can see here I made like 2 slices of my pie already. So there's not an atom here at this base. There's no atom here, up like at C/2. However, if I were to draw my next triangle base here, there would be at C/2 an atom here. And then there's one more atom over here that goes down to its triangle. So the total number of atoms is going to be 3, because those are completely in the volume of this hexagonal unit cell. So there's going to be 3 plus each of these atoms at the corners. Volume-wise, because of they're in this hexagon structure, contribute 1/6. So you have, or is it, yeah, 1, so 1, 6, 3. Yeah, so they each contribute 1/6, but there's 6 of them, so you have 2 top and bottom, and then you have 1/2 of an atom on the top and 1/2 an atom on the bottom. So there's going to be 6 atoms in an HCP. You also have to remember this is, I think, the first time that we deviate from the cubic structure. So you have a lattice parameter C and a lattice parameter
A. So for the HCP ratio, did anyone have trouble with the HCP C to A ratio? Did anyone do it for homework? Okay. Yeah, that's one way. To be honest, no one, like, every time I have to prove it, there's actually several months in between I have to prove it, so I usually go look up online. There are very generous PDFs available that should prove it to you. So it's simple geometry if you want to prove it to yourself why the ratio and closest packed is that way. If we have time at the end, I can look it up and try to explain it. But I have a feeling we're going to get stuck on the planes and directions within a cubic. So, oops. Okay. So any questions on that highlighted topic? Anything that, okay. So I guess we need to then talk about the diamond cubic structure.
Where did the 2 come from?
The 2 came from, so this is split into 1 atom and 1 atom, but there's 1/6 times 6. So it came from the top, so the top number of atoms and the bottom number of atoms. Just these though.
And one is for the 1/2 on the top.
Right, because that comes from that one. So the diamond is a unique structure in that it is technically referred to as 2, I believe, if I remember this correctly, it's 2 FCC lattices. So the reason I'm trying to remember if that's the right way to say it. So one of the other, I don't know if it was mentioned either, but we can only consider a unit cell if it contains the same atoms associated with it. So if you have different structures,
that technically have different atoms, the standard is even though it looks like a BCC and the center atom is a different atom, as we'll see later, it's not a BCC. It's just how they standardize it. So a diamond has all 8 corners. A diamond also has all faces. So I'm not drawing this to scale because then I would have atoms touching. And it also has what makes it so strong is this unique bond between the face atoms and the corner atoms. So if you were to go 1/4 the distance along A, so A over 4, in each direction, so this atom is inside the volume of this lattice structure. You have this atom bonding like so to the 3 other atoms, and you have that so it's a mirror image depending on how it's drawn. So you have that as a mirror image, but then on the opposite surface it's rotated 90 degrees. So if I have atoms here and here interior, the atoms have to be here and here interior. So there has to be an atom here interior that gets bonded with all the directions, and then you have to have an atom here, which is kind of hard to see just from my drawing. And so that, I guess, brings me up to to that next topic, which was in the email, which is the different lattices. Yep.
What are we trying to illustrate in
This picture, diamond.
that? I mean, like, what are all the arrows drawn?
Those are the bonding locations. So this atom is bonded here to this one, to this one, and to this one. So this atom does not bond to that atom, or it doesn't bond to this atom. So these 3 that I drew arrows to are its nearest neighbors. Does that make sense? So yeah, that would be, I guess, more straightforward to say those are its nearest neighbors. And so just to mention, we have NaCl. So NaCl is almost like two face-centered atoms, or how do I want to say this? Yeah, so it's almost like 2 face-centered atoms. So I have 2 colors, okay. So you can look these up online from that email. And so if we drew a center atom here,
corner atom somewhere over here. It's like it's going to be hard to draw 3D now. There's one there. And let's see. And so the reason why I say it's like an FCC, looks really awkward. The reason why there's an FCC interchanging lattice
is because so the reason why we can call it a face-centered with a face-centered is if you look at just the green atoms, their locations are at the face-centered locations. That's okay. Now, if you want to think about it, if for the blue atoms, if we had an extra plane somewhere, so let's say there's an extra plane in the back, we would technically get a blue atom, a green atom, and a blue atom. And so you can, if you can kind of imagine that, this would be blue, green, blue. This would be green, blue, green, blue, and green. And so what you can kind of see then, what happens is that you are putting a face-centered lattice of the blue atoms.
So it's two face centers?
So that's why they say, and that also goes back to kind of the standard that we're saying it's two face-centered superimposed on each other, supposedly, because you can only use the same atom to designate that kind of structure. Okay. So CSCL.
Test. No. Test. It works now? Oh, lovely. Okay. So where were we? We were...
So in this case, it looks like it's a body-centered, but we have one atom that's different than the other atoms. So you can, if you want to remember body-centered, that's fine, but the standard is not. So that's
CSCL, and then so you can look up the last one. Oops. Which is zinc sulfur. So we covered diamond, we covered that. Okay, so now we're to the point where I think this is what becomes the most difficult for some people, which is the crystal coordinates, directions, and planes.
So the crystal coordinates are not too difficult. You just have to set them. So usually when you draw your structure, you don't have to. I set the back corner as my origin. So you don't have to, but that's my origin. And then of course you have the rest of your structure here. There might be some standard just to make sure everyone's on the same page, but I usually start in the back corner, and you have to label your X, Y, and Z. So remember the right-hand rule. If I label this X and this Y, this is positive Z. If I did it the other way and I had X here and Y here, using the right-hand rule, that would be positive Z going down and negative Z going up. So if you were in physics 1 or 2, I'm also a physics major. That was my undergrad. We are very adamant about that. So right-hand rule, if you're putting X and Y, make sure you know which way your positive Z is going. So if that's the case, we really only work within the structure. So the idea is if we're drawing a vector now, that this vector uses the brackets notation, and this would be 0, 1, 0. And what we're doing is we're giving it a unit length of 1, so this 1 is the length of a lattice parameter. Not too difficult. So if we went, if this was a 2, nothing really changes because we just go and extend this further, but we're only looking in the crystal structure, the unit cell. So since we're only looking in the unit cell, we stop here again. Even though it's twice as long, if I wanted to designate that in our unit cell, all I have to worry about is that. Now, it might get a little bit more complicated, which should not be on your test, but just a small tangent is like if there's not an atom here, and it is technically too long, then maybe your unit cell is wrong. Something like that. Okay, and so so we can do some other different stuff. We can do along this back diagonal here, and we can use bracket notation to also say now we did not go in any direction in the X direction. We went 1 in the Y and 1 in the Z. So it's very similar to vector addition, where each is 1 unit length or one atomic lattice parameter.
Sorry. Trying to get to the galaxy is awesome.
Can't talk right now.
So there's this idea that, okay, so I guess I'll just draw the last one really quickly before I answer your online question. If we go from here to the corner, so corner to corner, that would of course be 1, 1, 1, right? We went 1 unit length or 1 lattice parameter each way. So then there's this idea, there's this notation that if I do this, which is the triangular bracket, or it's probably a different word for it, and I do 1, 0, 0, this technically means all possible arrangements of 1, 0, 0. All of them. So I'm only going to do this once. That means I can do this one. That means I can do. So now I'm drawing each one. That means I can do.
So what's the difference between the brackets and the lesser and greater signs?
This is including all possible combinations.
Okay.
So I'm going to draw. I'm not going to draw. I'm going to
just
list.
one.
Yeah. So this, you can have 0, 1, 0. You can have 0, 0, 1. You can have 1. You can have 1 bars. You can include the negatives too. So you can have 1 bar, 0, 0. You can have 0, 1 bar, 0, and 0, 0, 1 bar.
All possible combinations of parallelness.
I don't think that's the way you want to say it. So for example, if he said draw all possible 1, 0, 0 with the triangular brackets, that means I have to draw not only this one that I drew here, I have to draw this one, the one in the back, one down, and one behind.
So what happens if there's more than one? So what if it's 1, 1, 0, say? Would you have to draw all the vectors corresponding to
So unless it says draw all of them, you don't have to, because what I have found is in some papers, is they really are only referencing maybe 2 of all of them. So what they do is if they're trying to reference more than one, they'll also use this notation. If you ever see this again in the future. So if they're really only talking about maybe these two of the 6, like when you're reading a document or something and they're only saying something happens along these 2 directions, they can use this notation, even though it also represents all of the other combinations, which I don't know if that's exactly good practice, but so if it was 1, 1, 0, you would have that this means all possible notations that you can possibly think of, including the bars. Okay? Any questions? Because this is just vector direction. Then we're going to talk about planes. Yeah.
Can you just give us an example of how it would look with the negative? Like if you draw it
So this one is a negative? Or?
Well, like the 0, -1, 0.
Yeah,
Like if
so
you
the-
draw it.
So the 0, okay, so better remember. So I guess we'll do that one. The 0, -1, or so the 0, 1 bar 0 is this one right here. It's that arrow. But to draw that in your unit cell would actually be moving it. So if you also remember what has been taught about vectors, usually in Physics 1, sometimes in, I think, Calc 3. So technically, this is my y direction, and I am really drawing the 0, 1 bar, so that's technically in this direction, but that's not in my unit cell. However, it has a head and a tail, so I can move the head and the tail because it always will remain its same direction and same length, and I can move it back inside my unit cell. So I can move this to here, and I can move this to here, and I can draw it going this direction in my unit cell.
So then wouldn't your y-axis, wouldn't it protrude out of the cell? Would that still work?
What do you mean by y-axis?
If you do move it, even though it's parallel in the same direction and everything, wouldn't the y-axis, I mean, you're essentially changing the point of origin, right?
So?
But I'm saying, would it still work even though the y-axis would be protruding out of the unit cell?
No, because the y-axis is still here. On a normal 2D graph, when I draw a vector from origin, wherever the origin is, doesn't have to be 0, 0. Wherever, I can move that vector anywhere I want on that 2D diagram. It does not change the original axis. So yeah, so this doesn't stick out. It's not like I'm moving my origin. Again, I can move the vector, not the origin.
If he asks us to draw it, do we have to move the origin, or can we just draw it out of the
Depends on your grader, actually. If I was grading and you just drew this, I'd probably give you half credit because it's not in your unit cell. And that, again, is just the standard, is you need to draw.
So what would be full credit for you?
That one that's in the unit cell.
drawn backwards.
And then how would you, like, would you just have to write the, like, where your origin is? Like, would you just, like, state it before the problem?
Yeah,
Like
that's what I usually do. Is I always, like I said, I usually always pick this back corner, and I might like write a big 0 there or something. So at least if someone were to ask me, I'd say, well, I put a 0 there for a reason, and I can debate it. But yeah, I usually just put it in the back corner because you can kind of work. You can do most of the stuff from the back corner, I guess, is what I've seen.
So by moving this vector, the vector is still 0, 1 bar, 0, but you have to draw the origin point and the arrowhead in the direction in that unit cell, and it's still.
So just because I move the vector does not mean the origin changes, but it is the same length and same direction. But now it's like it's completely within my visible. I'm using quotes because it's like if I can only see what happens in this unit cell, only inside of it, then I only see this arrow inside of it. So I mean, it's kind of like a standard thing. So you might see other textbooks that are okay with it. I have not been too up to date, but usually very highly the standard is to move it in material sciences. They move it back inside. Yes.
So you're not allowed to have fractions in there, right? So what if you had one that was like 0, 1, 2, and that's bigger than your unit cell, right?
Mm-hmm. So that's a good question because I might have skipped that. So if we have, what did you say? 0, 1, 2?
Yeah.
So it's going to be different than planes. You cannot see what I'm drawing. Oh, I see. Okay. Yeah, some of you are a little confused probably. Oops. So for some of you online, I guess I was pointing to, so you can see this, right, online. So I was pointing to moving this vector over to here. Inside. So back to your question. 0, 1, 2. So we're going 1 in the y, and then 2 in the z. So when it comes to moving, we're still doing vectors. So it's like if I had another lattice above here. So if I had another lattice, technically, because it is repeating. If I go 1, 2, I draw the vector as it is to this location, but then I look in the unit cell and see where it stops, and that would be my vector. So as you can see, technically it looks like it's going only halfway in the original unit cell. But that's because if you were to extend the length fully, it would go. So this is the 0, 1, 2.
So when you draw it, would you erase the arrow that continued?
But I mean, I would draw it like this first because that's how my brain thinks, right? Because it's just vectors. So I just add one vector, and then I would add 2 of the other vector. But then I have to go back to this idea of there being everything inside the unit cell. Okay. Good question. I might have forgotten that. Yes?
So what you're saying is even though it says 0, 1, 2, you would draw it as if it is 0, 1, F1?
So basically, wouldn't the easiest thing to do would be to divide by the biggest whole number, and then you'd be able to get it that way? Okay.
There's a reason we use integers, though, and the reason we use integers is because when you start talking about using these values, HKL, and stuff like that for Bragg's diffraction and for some of the more complicated things, you don't want to do 1/4 the squared, right, and get fractions. So that's why we make them integers. But yeah. Okay. Let's check our online buddies. See how they're doing. Nope. Should be as it was drawn. I don't think I would ever ask you to draw that. I mean, it would be a good test of your understanding, but they're asking if I basically had a -1 and a 1, so basically the same vector along the same path. No, so R sharp 1, no. Shouldn't it be longer on the y-axis than the z-axis? No, because what I'm doing is R sharp 1 is I'm putting it back in the unit cell. So yeah, we'll talk about planes now.
So for planes, so I guess that was, so we talked about coordinate systems,
Which is just saying you can I usually put the 0 in the back corner, and then everything becomes like a normal 3D coordinate system, but you have to, there's a lattice constant available.
then we talked about vectors using the lattice constants supposedly to move along each direction in the unit cell. Now we're talking about planes. So if I have planes, it doesn't get trickier. It's just got to remember it's not like vectors. So if I have so we also use the bracket. We also use a notation of parentheses. So if I was drawing the 1, 0, 0 plane, that would be the face of the cube facing us. And the way that works is the idea of inverse. So I'm at a location of 1 always. So my x is always going to be 1. However, I'm going out infinitely in all directions. So this goes back of the inverse idea, why we do 1 over something usually. And it's a standard. It's just really how we understand how this is working. So this is really drawn as 1 infinity infinity. But if I do 1 over 1, 1 over infinity, and 1 over infinity, I get 1, 0, 0. So the same idea goes to drawing 1, 1, 0. So this idea is I go to a point location, so I'll go 1 here, and then I'll go 1 here. So these are more, the way I think of these are more like point locations within your lattice. So I go 1 here and 1 here, and I'm going infinitely in the z. So I know all these points are included. I know all these points are included. And since it's a plane, I have to know that all the points along here are included.
Okay, so I guess we'll go right to what their question was. And one, yeah. So if we do the 111 plane, I haven't used green yet. So the 111 would be 1, 1, 1. I'm sorry, 1. So 1, 1, 1. And that would be your plane. Because if I'm located here, you're directly in this plane of this point, and directly still in the point of this. Bless you. Any questions so far on planes? Yes.
So does that plane also extend infinitely in every direction, or is it just the triangle?
So this does extend infinitely in all directions, but it's only contained in the unit cell right now visually. That's why it looks like a triangle. So this is usually the hardest thing. Does anyone have any like unique questions on this? Yeah. Yeah. So that's where the inverse comes into play here as well. So the question was, what if we had something like? Well, I think someone asked a good question. I guess they had one. What is the 0, 1, 2 plane that has a little bit of everything in it? So we'll see if I don't make a fool of myself. Okay, so we know that this extends infinitely in all directions. We know that we got to go to a location of 1y, and then we need to go, in a sense, to a location of 1/2. Why? The reason it's 1/2 is because this is normally drawn as 1 over infinity, 1 over 1, and 1 over 2. Or that's how it's understood. So that means we got to go 1/2 up in the z direction. So this would connect here and here. I know it extends infinitely along the x-axis, so I know it has to obtain those same 2 points, and then I can connect it. So this plane is moved. It doesn't extend all the way up on the z-axis.
Why are those brackets?
Because I wasn't paying attention. And so I guess just to mention too that if you're including all the possible planes, you use what's called the curly brackets. Just to mention that's if you see the curly brackets, they didn't misnotate. It's not like they forgot to put parentheses. They really mean something different. Any other unique questions on planes? So they want 1, 1, 1 bar. Okay. So again, like with usually what happens, or I didn't say usually, but what can happen is if you have a plane that is not extending in your unit cell, you have to move it because it's a plane, it's a repeating plane. So it's repeating at a certain d spacing, as we'll learn in bracket fraction. So since it's repeating, you can move it in a sense over if the length is the same. So in this case, it would be, there definitely has to be intercept here. So again, sorry, my 0, my origin, my x, my y, and my z. So starts, we go 1, we go 1. And then this one would extend -1. So that would go down. So my plane technically would look something like that.
So if I redrew it back, if I redrew it in my unit cell, it would look.
Wait, do all coordinate planes have to have at least one of the numbers with like a line above it?
I'm sorry?
The third one has a line above it.
So what does that mean? It means negative.
Okay.
Yeah, it's a notation thing. So if I move it back into my crystal structure, this would be the 1, 1, 1, or 1, 1, 1 bar.
So for the 1, 0, 0, I can't pick another face plane because you didn't use curly brackets. So if you use curly brackets and you just had 1, 0, 0, then you could mean any plane you wanted on any face of your cube for Jason. And so if you use just the parentheses brackets, you have to specify only that plane. If you're using curly, then you can specify any, in this case, any plane you wanted. Calculations, so are there any calculations I didn't talk about for? Because I can think of some, but I don't know if you learned them. So did you do shear?
Can you just like do a problem that would involve something like this? I understand it, but I'm not quite sure like how it would be acted.
So what problem? Is it a homework problem, or was it? Did you guys learn about shear? Okay. So you learned about Bragg diffraction? Yep. Line defects, Berger vectors, grain boundaries, point defects. So we're moving right on track. We're doing good time. Did you have something, or did you want to wait till the end of?
I'll wait.
Okay, fine. So X-ray diffraction and Bragg's law. That's what we're going to do now. And so, let's see, anybody online? He showed us how to find the angle between planes and directions. Coulomb's law. Okay, so you guys are, what is it, spring? So you all took physics 1, right? Yes. No, you didn't take physics 1 back there? No? Okay. So the things I think you should have come across anyway is the dot product, right? Did they do the cross product for you guys taking it now? Did they? So those are the two ways you can determine angles between vectors or planes, if that makes sense. So the dot product, if you don't understand the dot product, ask me later, but it's the basic math is you can do the dot product equals, remember, the magnitude times cosine of an angle. And so you can determine the angle. So that might be a calculation. I don't know, but someone reminded me that was a possible calculation you might have to do with vectors or directions. Yes, okay, so Bragg. So if you go to, let's see here, what is it? Tutor track? Reviews. So I had a PDF I created, I think, a year ago that had a good number of topics on it. So I'm trying to see if I can find it and bring it up for you. Where's the old one? They changed this on me.
When's your test again?
Tuesday.
So I will ask stuff you don't need right now. Some of it is stuff we talked about. Okay. So the Bragg father and son duo were able to determine using this newly available source of wavelengths called X-rays. They were able to determine with very crystalline structures, very repetitious structures, that there was this relationship available. I guess I'll just do the proof really quickly. So they noticed that from physics as well, this idea that if you had a incident X-ray with a certain wavelength, and then there was another wavelength that came in for the next plane or the next atomic spacing, for a specific plane, they noticed that if you got this ratio set up so that this length from here, this dot, all the way over here, so this entire length equaled another wavelength, you would have what's called constructive interference. So this idea is that this wavelength, as it enters here, I should probably use a different color, as it enters here and leaves here, would be in direct relationship with that wavelength there, and the relationship would be that it's in phase. So there's no change in the wavelength whatsoever. It's the exact same type of, there's no phase shift, if you know what that means. So the wavelength comes in like this on the top, and so maybe we're talking about here is what we're talking about. The same wavelength would be able to have the exact same looking curve as it leaves. That would be constructive interference. If this was shifted by something, then there'd be maybe what's called deconstructive interference, or some kind of interference of some nature. So the theory goes that for complete constructive interference, we get this proof right here. Is that small for you guys back there?
So this idea gave us this notion that 2D, where D is the spacing between planes, so it could be really easy spacing, so it could be the lattice spacing if we hit it right, or it could be some other spacing where if we notice when we drew our planes, there could be an even smaller spacing between a repetition of planes. And so the reason why we have n lambda is because you can have, in this triangle here, you can have, how do I want to draw this, I guess? You could have one wavelength, or you could have two wavelengths. So you could have it go exactly half. It's a little messy. It's very messy, actually. So you could have one wavelength. So I'm just drawing a sinusoidal curve, or you could have two wavelengths. So it gets cut in, or it gets cut in half because you have to fill up twice the number of wavelengths. However, no matter what's happening, you would still get complete constructive interference. So the waves would not attack each other in a way to negate. With that being said, they also proved for cubic structures this relationship that the D, the spacing between planes, is related to the lattice parameter divided by what's called these Miller indices, these HKL values. And this goes back to this idea that we don't want to use fractions just because the math becomes simpler. You know, they just saw that ahead of time, and so they made all the work visible right away, so that the math did not have any fractions involved, and for the HK and L exact values. There are more complicated relationships for D if it's not cubic. So for HCP, there's a more complicated relationship. Then when you get into the really hard stuff, that you have your structure shifted by an angle, or you have so your lattice parameter is not the same.
Are these equations only true for cubics?
That is correct.
Both of them are only for cubic?
So the left one is always true. The left one will always be true no matter what. And the left one allows you to see, well, I don't want to say I guess it allows you to see, but it allows you to calculate your planar displacement. So if you do the actual diffraction pattern, so the diffraction pattern can look something like, so you can go along and boom, you have a really high spike, you go along, get another spike, and you get something, and then you don't get anything for a while, and get a little spike there, maybe, and then boom, another one. And another one, and then you get some weird stuff going on down there. So this is a diffraction pattern. I believe you should have seen it somewhat or briefly in class. This idea is that you can measure 2 theta. The 2 theta comes from this idea, from the fact of how your X-rays are collected, are counted to give you this intensity on the far left here on your vertical axis. And so this comes from this 2 theta is double this angle. And the reason for that is if you have your specimen and you have X-rays being shot at it, if you move it an angle theta, so if it's being shot at and we move it a new angle theta to get a new angle on it, to get different plane spacing, your collector has to actually move 2 theta. So the collection, it's all based on the collection unit, is why we have this 2 theta on the bottom. Your collector, if you move your emitter an angle theta, your collector has to move an angle of 2 theta to actually collect the X-rays that are constructively being bounced off, or I guess I will say bounce for now, being bounced off from the specimen. So this is always true. So if you have this, and you know what type of wavelength they're using for X-rays, you can figure out where your peak is, where you have a very strong intensity, because that's where there's some constructive interference happening. So you know there's a plane that has to be there. If that's the case, you can always calculate your plane spacing. So even if you just have this, you can at least know the spacing between planes. You might not know what those planes are or where they are located in a unit cell, but at least you know the spacing between them. Then it comes from more of a theory-based calculation of whether or not you're using a cubic structure or you're using some other more complicated structure. If that's the case, then you can figure out maybe not only your lattice parameter, but also where this plane is located in the unit cell, and maybe how complicated it is. So combining these two gives you the lambda over 2a squared equals sine squared theta over x squared plus k squared plus L squared. Any questions? Sorry, yes.
So if you were going to solve that first example right there, what would you do about like the n in the equation?
Usually you can set it to 1. And I think Callan tells you to. Professor Callan will explicitly say n equals 1, so there's no confusion. He rarely has anything that would cause confusion. So if you are confused, it means you probably need to know it or something like that. I think, yeah.
So what does D equal exactly? What's it stand for?
It is the distance between planes. So for example, if I was looking at, an easy example I suppose would be if I'm looking at the interplanar distance between the top and bottom faces of a unit cell. If the lattice parameter is A, and I'm looking at those 2 planes, that means the interplanar distance would be A. Then when you kind of change your plane a little bit and you get the different abstracts, then you have to think about, okay, there's a plane there in my unit cell, but then on the next unit cell there's another plane there that I can draw, and then that becomes the spacing between them. Okay. Any other questions? Any tangent questions to this that that you may think are related but not exactly related? Okay. So usually this is, I feel, just plug and chug. We can take a quick look and just see. Let's see. Yeah. So if you know, I mean, because Professor Callan is also, I don't want to say part physicist, but he has physicist training and background. As you know from physics, and we like to throw not necessarily curveballs, but we like to include past topics on you. So a lot of questions are going to include multiple parts to them. They're not going to just go plug and chug. Sometimes they are, sometimes they're not. So for example, for this, I just noticed for this question down here, you're given the atomic radius and you know it's FCC, so you should be able to calculate the lattice parameter.
Can we do that?
How? Yeah. It goes back to the previous idea that there's a relationship between the two. So the lattice parameter A for FCC is equal to 4 over square root 2R. This diagonal here. And if that is the closest relationship, so if this is A and this is A, then you do the triangle and you get square root of 2A as the total length of this, and that has to equal 4 radiuses of your atoms. So 4R
over square root of 2 equals A. So there's going to be stuff like that easily. A is lattice parameter. Well, fire alarm. See, so that stinks. He showed us how to find the angle between. Okay. So I think we're almost done in terms of concepts because I don't think the rest of it is too. Where'd that go? Math intensive. Start. Okay, so we're almost done. Okay, so that covers X-ray diffraction and Bragg's law. So your point defects are three. You have substitutional. You have your vacancies. And you have your interstitials. So a substitutional atom, I guess I'll add one more. So a substitutional atom can be either what's called a self-substitutional. So one of these same atoms can self-substitute it into a location where it doesn't belong. And I have them overlapping, but what would happen is it would bulge the material there. So it would try to stick itself in there and the material would bulge around it, so it wouldn't overlap like I have drawn here. Another substitutional is this idea that if you have atoms of very similar sizes and what was the other thing? Ionic. I forget what the chemistry term is, but it allows it to bond very similar. They have very similar ability to bond. This is technically a different atom, but it's able to fill the same location in the atomic structure because it has very similar size.
So like silicon and carbon?
No, because carbon is usually very small. So carbon actually goes to our next topic. So usually like, what was the example? It was like nickel and something. Can't quite remember. Because carbon goes into our next topic. Because in materials, and if you're going to be a mechanical or aerospace engineer, you're gonna work with titanium, aluminum alloys, or definitely probably steel alloys. And in steel alloys, it's this idea that carbon is actually what's called an interstitial. It's able to fit in. It's supposed to be a dot, not really a line. It can fit in between the atoms. So one of your homework examples was this idea of, can you prove what the largest atom size is in an interstitial location? So if everything was normal, the lattice was normal, what is the maximum atom size you could fit into that location? And I think it was a carbon atom, and I think it was something like you got a certain size, and then if you went online and you found the atomic radius of carbon or something, you would compare the two values, and then you would know whether or not it fit for that specific arrangement. And then the last one is vacancies, and that's a somewhat huge deal in atomic lattices. Let's see if I can actually. So is this? So a vacancy is a missing atom at a location where it should be. Okay, so those are what's called our point defects. This also leads us to a good transition, because one of the topics not covered on there, which I think will be, which I believe will be on the test, is the vacancy concentration as a function of temperature. So for vacancies, we have this relationship where we have n, the number of vacancies in a lattice, compared to n sub v, the number of vacancies in a lattice, compared to the total number of atomic sites. So in this small diagram here, I have a 4 by 5. Yeah. So I have 20 atomic spaces here. That's my total number, so that would be in my denominator. The n sub v would only be 1, because I only have the exponential of negative qv. So this is Q is energy, so that's going to be in joules. If it's in kilojoules, you have to make it into joules. It's SI units. So it has to be in the SI unit of a joule. Well, it's not really an SI unit because it's made up of SI units. But that's the amount of energy it takes to make this vacancy. So at room temperature, there's a certain amount of energy is required to make these vacancies. As the temperature increases, so this is now RT on the bottom. As the temperature increases, the amount of energy it takes to create that vacancy.
What does R stand for?
R, you said?
Yeah.
R is the Boltzmann constant? No, that's K. Should have been given to you. What is it again? K is Boltzmann. Oh, it is the Boltzmann constant. No, that's not the Boltzmann constant. The gas constant. So
PV was in RT.
yeah, so it's the same R. It should be K, you made it R. I believe it's R. It's RT, not KT. Subscript on Q is V for vacancy. Yeah.
What's EXP?
EXP is the short, so it's just E. But in some programming lingo and for shorthand, it's E to the power of something.
Oh, okay.
Yeah. So this is E to the power of negative Q over RT. So Q doesn't necessarily change because that's the energy it takes to create a vacancy. At different temperatures, you can have different ratios. So you can have you can have more or less vacancies. So this is an important equation. Can you all read this, or do I need to write this on a?
Yeah, that's E to V with -2V over R.
So Q sub V. The V, just to remind you that energy is for vacancies. So
Wait,
it's
what's this equation?
for vacancy concentration.
So the Q is
So it's like a subscript. So it's telling you that Q is meant for if you were given just multiple energies for some reason.
just the Q is for.
It's the energy associated with creating a vacancy. Not necessarily at a specific temperature for the simple examples, just the energy it takes. So usually that's given to you.
So it is.
K. What?
Wouldn't the R be K? I'm just looking back to my notes, that's how it's K.
Yeah. Vacancy. I hope the book I wasn't using was really old. It's brand new. Let's see. Okay, so my bad. So that is Boltzmann's constant. I'm just putting a little b there for case of b. So again, not again, but to remind you, just be really careful on your units. So whenever if I were to answer a question or say something, whenever I say unit analysis, that's just telling you, please check your units and make sure all the units cancel or all the units get to the correct unit you're looking for.
Is temperature, would that be in Celsius or Fahrenheit? Does it matter?
Neither. It would be in kelvins. It's in the absolute. So that's a good point. Remember, temperature has to be in kelvins. For those online still, temperature has to be in kelvins. It's an easy mistake. Usually joules. I'm trying to remember, Mark. So Mark, it can be if your Boltzmann constant is an EV, because remember your Boltzmann constant can be an EV or J. I think that will answer that question for you. So that's another good point is depending on what type of K or Boltzmann constant you use for the situation, if your K for some reason was given to you in electron volts, which it is a joule, but it's for very small energies, then your Q has to be EVs. And this goes back to the idea that please just make sure your unit analysis is working out okay. Especially because like a couple knowns, that might be one of them. I don't remember. More than likely, though, even in the question in the parentheses, he might say, remember this is this, this, and this is. So this will be on the test, even though it wasn't in that email. So you all know how to work with natural logs and exponentials. So you know that the natural log of E is 1.
So the idea is if I have e to a certain power, and I take the natural log of it, I can move this power to the front. It's one of the properties of natural logs. So then I can get, so if this was a number, let's just I guess call it c. I can move c to the front and I have natural log of e. Well, we know this is 1. So we're left only with a constant. So this goes back to just, I call it basic math. I can't remember when you learned it, if it was Calc 2 or if it was Calc 1. I think that's all you really should know. Does that make sense? That is correct, yeah. Equating both sides. I forget what the math term is. Keeping the equation equal or something. Okay, so let's see if there was. So we talked about point defects, which led to vacancies, which led to vacancy concentration. So we'll talk about line defects. Do you remember what the 2 line defects are? Anybody just want to shout them out? I heard screw. That's one. And edge. Yep. So there's a screw and an edge dislocation. I'm not sure for the vacancy concentration what he would give you. There's just too many, there's a lot of variables, so there's a lot of different scenarios he can do, which is why it makes a good problem arc online. Let me finish up, Adam, and then I'll see how much time I have left. Because we don't have a whole lot left, I suppose. So a line defect, so if we're talking about an edge dislocation, if you have a bunch of atomic arrangements, so there's atoms in here, very small, so it looks like a line. What happens is if I include a plane of atoms that don't necessarily belong, or in a sense are added due to the way the crystal cools or the way the cooling process works, is there just happens to be an extra plane of atoms where it doesn't belong. This is known as a edge dislocation. And so an edge dislocation has an extra plane looking at a 2D environment. So the reason why it's called an edge is because you have to look at the edge of something to see it. For a screw dislocation, it makes I'm going to say it verbally, even though it may not make sense visually. It makes a hexagon or a helix of atoms that move along the line. So remember, this is a line defect. So along the line defect is this helix of atoms that are not quite in the same arrangement as they should be. So this one, I recommend maybe looking up. Maybe I'll look it up online right now because it's hard to draw. Oh, that was a good one. Go back. Maybe not that one. Where are you?
So the yellow and red in this case are just the normal atom positions. However, the green and blue are what are considered the helix, the helix, the atoms in a helix. And so what's happening is this is created by shear. So when you create shear along a certain direction, if you want to think about it, there's a certain cut that's made up into a certain point where the line occurs, and so there's this continuous. Oh, that's a bad color. Let's use green. If there's a continuous. Oh, that's even worse. What happened to the blue? So what's happening here is there's like a continual atom helix going on. So there's this kind of helix motion if you were to draw a straight line that goes through the line defect in a crystal. And the reason it can be seen that way is because atoms on this side are in all perfect crystal order, and all atoms on this side are all in perfect crystal order. It's just these atoms. It's just these atoms in this region that are being shifted due to the shear stress on the material at that given localization. And so by doing so, these atoms are shifted out of their normal locations. And in this case, it's just two atoms. You can have more depending on the actual zone of this helix. You may have more, but usually it's just, I believe it's just one or two atoms. Anyway, it's this idea of you're shifting things, and because these atoms are being shifted by a shear, they're moving and being displaced. To think of the Burgers vector, the Burgers vector is this idea of quantifying the displacement associated with this line defect. I'm going to say that again. The Burgers vectors allows you to quantify the deformation that a line defect occurs on the crystal. So in this case, your Burgers vector would be if we were to shift everything back into normal location. So they may have mentioned the counting method. So if I count 1, 2, 3, 4, and then I counted a certain number, there, and then I had to go back a certain direction. There's the next. Let me get out of the way. The next location of planes is here, not here. So I have to do 1, 2, 3, 3, and then if you go up, you would get to a new location on the lattice that is off by a certain distance for an edge dislocation. That distance is quantified as the Burgers vector. So the distance, I don't know how detailed you went into it exactly, if you wanted you to know like quantitatively or actual, but the Burgers vector in a sense is just the deformation quantized on what a edge dislocation does for you. And in this case, because it's a shear displacement, it's being a shear displacement in this direction, your Burgers vector would be parallel to the line defect. So your Burgers vector is parallel to the line defect because your atoms are being sheared, so they're being displaced this way. But because they're being displaced that way, it's creating this helix effect. And because the deformation is happening in that direction, your Burgers vector is parallel to the actual defection line. In this case, your defection line is into the board. So if I were to continue to draw this in 3D, there would be this very long line of dislocations occurring at this place. However, your Burgers vector is parallel.
So it's not parallel, sorry, it's perpendicular to your line defect. So if anything you want to take away from point or line defects is that for a screw dislocation, your Berger's vector is parallel, and in an edge, your Berger's vector is perpendicular to the line defect. Any questions on that? It can be quantified. So it usually goes, well, I say usually, but it can be quantified. I don't know if it's going to need to be quantified for this level of a class, but the Berger's vector can be quantified, and it's usually along the direction of closest packed atoms because it deals with slip. So I don't. That's why I think if anything you want to take away is the idea that when something is in edge, the Berger's vector is perpendicular, and when it's in screw, the Berger's vector is parallel, the actual line defect. Okay, so then that brings us to our last point, which is grain. I think I'll go online for this, which is grain boundaries. Any questions? Yeah, sorry.
So Berger's vector, if the magnitude, it says it'd be equal to an atom's diameter. Could we find the diameter by using, like, let's say if it was like space-centered cubic or something, and how we would find the radius by 4r equal a square root 2? Could you solve for, and then just multiply by 2 to get the diameter?
Yeah.